Good morning. Good morning, AP Physics 1 class of 2021-2022. So first things first. Normally, I would post your work at 8 a.m. every morning. So starting tomorrow, I'll be posting your day's work at 8 a.m. That way you can plan your day, see what you want to do first, what teacher's work you want to do first, and etc. Secondly, when submitting your work, take pictures and scan them using a scanner app, and then attach them. We're not using the workbook today, but when we start using it, same thing, you will take pictures of the workbook and scan them using your PDF app and then post them as a single PDF file. Yeah, at some point, I'm going to look at the Google Meet schedule to see when you guys have Google calls or video calls with other teachers, other classes, and then I'll also put video calls for our class. I want us to have at least one, but preferably 2 video calls a week. I will also invite at some point students who did AP Physics last year, so they can tell you how they were able to do AP Physics and get good grades or get bad grades or etc. So I invite some of them to talk to you, maybe on a video call or some other way, if we're back in person. So unit 1 is one-dimensional kinematics. One-dimensional kinematics, 1D, one-dimensional kinematics. And that's where we're starting. Kinematics, you might look at that word and think, what does this even mean? The word kinematics is simply describing motion. So we are describing motion, right? That's what kinematics is. So you can also think of this unit as linear motion, because a line is one dimension. So this is linear motion or one-dimensional kinematics. The basic idea here is that we're trying to describe motion. We're describing motion of an object, of someone, of anything. That's what we're doing. If I asked you a question, are you moving, right? Are you moving right now? Are you moving? What would you tell me? If you're in a car going somewhere, you could say, yeah, I'm moving, because I'm in a car that's moving. If you're sitting at home in your bed or somewhere doing your work, you could say, no, I'm not moving, I'm just sitting. If you are, if you like thinking about space, you could say, well, I'm sitting on the earth and the earth isn't moving. So yes, I am moving. Or someone else could say, I am sitting on the earth and the earth is spinning, so I'm spinning, so it's spinning motion. Technically, I am moving as well. All of those descriptions of your position of where you are correct, and all of them are descriptions of the same motion. But the important thing is we need to be aware of a very important idea in physics, and that's called a reference point. Reference point. Each of you has described, or any of the answers that you could give to describe your motion right now could be correct with respect to a certain reference point. If I look at someone on a bus and I can say that person is moving because I see the bus moving, my reference point is the street or wherever I'm watching that person from. But to them on the bus, they are not moving because their seat is stationary. So with the reference point of the bus, they are not moving. So it's important when describing motion to be aware of what reference point we're using. Some of the ideas that we're going to talk about will be displacement, vectors and scalar systems, time, velocity and speed, and then acceleration. So let's start with displacement. To understand displacement, we need to first understand position, right? Where an object is in a plane, I'm sure you've heard about the Cartesian plane. The Cartesian plane is the XY plane, right? There's also a 3-dimensional plane. If I add the z-axis, that's the 3-dimensional plane. Where an object is, wherever the object is on any plane, is its position. This position could be 4 units on the y and 2 units on the x. So that's an object's position, right? An object's position is, in physics, we represent the position with the letter x. X is position. And if I put X bar at the top, I'm going to talk about what that means in a bit. Then that becomes a vector quantity, which we're going to talk about. I think you saw that one of these things was vector quantities. We're going to talk about that. So every time position changes, if there is a change in position, that's what we call displacement. Displacement is a change in position. Make sure you're writing down these important ideas. So when position changes, this person could have been at this position, original position x0, and then they move to a new position x1. Their position has changed, so their change in position is their displacement. So their change in position, which we call displacement, the delta symbol or the triangle represents change in physics. If I want to get that change in position, I'll get their final position and I subtract their initial position, right? That will tell me their displacement, how much they've been displaced. I think you can visualize it. If you displace your mouse or your cup, if you simply get its final position and subtract the initial position, then you'll be able to tell how much you've displaced that object. Now, displacement and distance, what's the difference between those two? Displacement, I hope you can see that when an object moves from position x0 to position x1, then my displacement is going to be final position minus initial position. That means it's taking into account the direction of the change in position, the direction of the movement, or the direction of the motion. So if I am interested in the direction of the change in position, if I'm interested in saying I moved from home to school, or I moved from Kampala to Jinja, then that is displacement. But if I'm only talking about the distance traveled, the length between 2 points, distance is the length between 2 points, then I'll just say I traveled 20 kilometers today, right? Just the value 20 is the distance moved. It doesn't take into account the direction because I'm not interested in specifying the direction. So distance is simply length between 2 points, or yeah, and displacement is the change in position. Distance is always traveled in a particular frame of reference, right? In a particular frame of reference. Like I explained this earlier. According to someone on the bus, right, they are not moving. Relative to someone on the bus, they look at themselves in the same chair for 2 hours, they will tell you, I have not gone anywhere, I have not moved. But if you're watching them from the side of the road, you can easily tell that they moved from one point to another. So I hope this helps you understand the relationship between position and displacement. Displacement is the change in position. I hope that you're able to distinguish distance and displacement. Displacement caters direction, right? Displacement is basically change in position with direction, or distance traveled in a specific direction. That's another way you can define displacement, distance traveled in a specific direction. Distance is simply the length between 2 points, and there's no direction involved. How are you able to calculate displacement and distance given initial position and final position? Well, displacement, remember I told you displacement is a vector quantity, so it takes into account the direction. However, distance is simply interested in the scalar magnitude. I'm going to explain these terms. The scalar magnitude of the distance that has been traveled, of the, yeah. So think of it this way. If you have Solomon right here, right? Solomon moves from here. This is the path from his home to school. He gets to school, right? His initial position is right there, where his home is. His final position is right there. Displacement is always going to be a straight line path, right? The displacement will always be a straight line path. So if I ask for Solomon's displacement, the question is basically asking, what is the straight line path from his initial position to his final position? So I'll just get x1 and subtract x0. That is the straight line path from his school to home. That's his displacement or change in position. But distance traveled is a scalar quantity. It's asking you how much distance did Solomon actually travel on these roads all the way until he got to school, right? There's some expressions that were used in the past, things like 2 days as the crow flies, or 2 hours as the eagle flies, or something like that. So those were basically referring to if someone asked you what's the distance between, oh, how long does it take to travel from Kampala to Mukono, and you said it's 1 day or 2 hours as the crow flies, that means if you went in a straight path from one position to another, i.e. displacement, that's how long it would take you. But I hope you can obviously see that if I'm going in this winding road and I'm counting distance traveled, then that's going to be a much longer distance. So distance traveled is not a vector quantity, but displacement is a vector quantity. Let's look at this example. We have a cyclist who rides 3 kilometers west, then turns around and rides 2 kilometers east. What is her displacement? What distance does she ride? What is the magnitude of the displacement? So this cyclist first goes west. We're going to consider west as negative direction and east as positive direction, right? Because west is on the negative side of the x-axis and east is on the positive side of the x-axis. So first they go west, right? Negative 3 kilometers. And then they go east, positive 2 kilometers. So their final position is right here, x1. And their initial position is right there, x0. I hope you can see that displacement or change in position will simply be final position minus initial position. Their final position is if you're counting final position, then you're counting it from the point where they started. So if the point where they started is 0, this point would technically be -1 because this is -3. I hope that makes sense. Their final position is -1. Their initial position is 0. So their displacement is -1 kilometers from their initial position. They've only been displaced 1 kilometer towards the west, right? That is their displacement. But what about the distance? What about the distance? What is the magnitude? Sorry, the magnitude of the displacement is, let's finish that. Oh no. We found displacement, check. Distance ridden, what distance does she ride? I hope you can see that distance, in order to get distance, we'll just add up everything. So the distance will be equal to -3, or since distance is a scalar quantity, distance will just be equal to 3 plus 2. So this person rode a total of 5 kilometers, right? Because, yeah, they rode a total of 5 kilometers. Magnitude of her displacement. Magnitude, I hope you remember from your math classes that magnitude is only interested in the size. So the magnitude of -1 kilometers is just 1 kilometer. So the magnitude of their displacement is 1 kilometer. Vectors and scalars. I've said a lot about this already, so let's just make it official. A vector quantity is a quantity that possesses both magnitude and direction. Or in other words, a vector quantity can be defined by its magnitude and direction. So vector quantities have magnitude and direction. And scalar quantities are only defined by their magnitude. Magnitude is the same thing as size. Let me give you some examples. Something like displacement, right? If I'm describing something's displacement, I'm going to tell you that that cup was displaced 2 centimeters to the left, right? So I'm telling you both its magnitude, the magnitude is 2 centimeters, and the direction, which is to the left. However, if I'm describing something's distance, if I'm describing the distance that the cup moved, I'll only tell you the cup moved 2 centimeters. I won't tell you in which direction because it doesn't matter, because I'm only interested in the distance. Another example is velocity, right? Oh, before we go to velocity, let's use other ideas. So let me just create a table here of vectors and scalars. Some examples of vectors: you have displacement, we've talked about it. You have velocity, it has magnitude and direction. You have any kind of force will have a magnitude and it will have a direction because it acts in a certain direction. You guys come up with 3 other examples at least and take pictures of that so I can see it. Scalars are things that only have magnitude, time. If I tell you 5 minutes have passed, you don't know where they've gone, whether to the left or to the right, but the time has been spent, so that's a scalar quantity. Distance is a scalar quantity. Wow, that handwriting. Other examples of scalar quantities can be mass, and you guys find 3 other examples and take a picture of that. So that's the difference between vector quantities and scalar quantities. Remember, vector quantities have both magnitude and direction. Scalar quantities have only magnitude. Time, velocity, and speed. I think we've already talked about velocity. Let's first talk about time. Time. What do you think time is? Like if someone asked you what is time, what would you tell them, right? We're not, like, we understand the concept of time, but what is time? Anyways, velocity and speed are all related to changes in position, changes in displacement, or changes in distance. So we've seen how displacement is the change in position. You have x1 minus x0, right? That's displacement, it's change in position. So velocity, if your displacement changes over a certain period of time, what you have is velocity. Because if me and someone are running and my displacement changes by 5 kilometers, but that change only happens in 2 minutes, right? Yet someone else's displacement changes also by 5 kilometers, but it happens in 40 minutes, then obviously my change in displacement happened faster than my running partner or the other person. So that means that there's a factor here. There's a factor here that has to do with time, and that's what we call velocity. So velocity, which is denoted by the letter V, the delta just means change. A change in velocity is the same as a change in this, velocity V is change in displacement divided by time. And therefore speed, V is V bar because it's velocity, speed is just V, is equal to change in distance divided by time. Change in distance divided by time. Going back here to vectors and scalars a little bit, when we're talking about vector quantities, we represent them with a bar on top to show that it has direction. It's very strictly speaking, it's supposed to be a squiggly, but you can just do a bar. And when we're talking about scalar quantities, then it's just the symbol or the letter symbol. So when I say x here, I mean distance, and when I say x bar, I mean displacement. So that's velocity and speed. Instantaneous velocity. If you think of a car traveling from Kampala to Entebbe, that car is going to go through a range of velocities. At some points it will be stopped, at some points it will be like going so fast on the expressway, at some points it will be going slow in traffic. So Instantaneous velocity is the exact velocity of that car at one single point in time. Average velocity, V average, is given by the total displacement divided by time. Instantaneous speed, just like instantaneous velocity, is the speed at an instant in time. Average speed is again total distance. So average speed is total distance divided by total time, or divided by time traveled. Yeah. How do you calculate velocity given initial position and final position and time? We're going to look at this example, and then derive a graph of velocity versus time from a graph of position versus time. Remember, this unit is one-dimensional kinematics, and kinematics is basically describing motion. Motion can be described using words or pictures, and pictures in physics means graphs. So I can draw a graph like this, and you've seen these graphs before in at least grade 10 math. This graph can represent the velocity of the object, and this can, represent the position of the object, and this can represent time, right? From each of these graphs, we can tell what's happening to this object. As you can see, the position is changing. As the time goes up, the position goes up, right? Is it going up at a constant rate? Yes. So since time is going up as position is going up, that means this object has speed, right? That means the object has speed. If I try to think about the slope of this graph, you guys remember slope is rise over run is equal to slope. The slope of this graph, change in y divided by change in x, is going to be change in displacement divided by time, or change in time. And I hope you remember that velocity was also described or explained by the same idea, change in displacement over change in time. So the ideas kind of come together always. The slope of a position time graph, what we have here is a position time graph. The slope of a position time graph is velocity. The slope of a distance time graph, if I had a distance time graph, distance time, the slope of that graph will be change in distance divided by change in time. Normally, every time we're doing change in time, we just use t because we consider 0 to be the initial time. So that's why a lot of the times we just simply write in t. So yeah, change in x divided by time, we know that that is equal to speed. So the slope of a position time graph is velocity. The slope of a distance time graph, is speed. Now, if I have a position time graph, and that position time graph is like this, right? What does that tell me about the speed time graph of this object? If you look at this, this is a straight line going through the origin. So that tells me that the rate at which the position is changing, let's say this was 1 second and this was 10, in 2 seconds this is going to be 20, right? In 3 seconds this is going to be 30. What does this tell you? If this is the graph of position versus time, then the graph of speed versus time for this object, remember, speed versus time, the graph of speed versus time, what will it look like? We know that speed is the slope of a position time graph. From quickly calculating the slope of this graph, you can see that that slope is 10, right? 10. And what have I done? What I've done is I have divided meters by seconds. I've divided meters by seconds to get the slope. So on my speed time graph, the speed will simply be 10 meters per second, right? Meters per second is the unit for speed. I did not talk about these units. The unit for speed is meters per second. The unit for velocity is also meters per second. The unit for distance is meters, and the unit for displacement is also meters. Okay, so this is how I can get a speed time graph from a position time graph. Let's look at this example. A commuter train travels from Baltimore to Washington and back in 1 hour 45 minutes. The distance between the two stations is 40 miles. What is the average velocity of the train? Average velocity. Now remember, this is velocity, and velocity is change in displacement divided by time. Displacement, not displacement. So change in displacement is going to be final position minus initial position. If you look at this train, it travels somewhere and then comes back, right? So it goes back where it started. So there's no displacement, right? No matter what the time is, even if it's 1 hour 45 minutes, there's no displacement, so its average velocity is 0. Finished. 0 miles per hour. That's its average velocity. What about the average speed? The average speed will be total distance traveled divided by time. And the total distance traveled is 40 miles, but it's going there and back, so that's times 2. And the total time is 1 hour 45 minutes, that's 1.75 hours, and you can get the speed of the train from that. This question wants you to find it in meters per second, so go ahead and convert miles per hour to meters per second. I hope you guys know how to do that. Acceleration, this is our last one for now. Acceleration, we've seen that velocity is the rate of change of position, rate of change of displacement, and speed is the rate of change of distance. Now, if the speed or the velocity is also changing as time changes, that's what we call acceleration. So acceleration is simply the rate of change of velocity. Let's recap. Speed or velocity is the rate of change of displacement. Rate of change of displacement. And it's given as speed is equal to change in displacement divided by time. Acceleration is the rate of change of speed or velocity. And acceleration is therefore given by change in velocity divided by time. When your speed is changing, that means your speed is increasing or decreasing, then you, in physics, we say you are accelerating. I'm sure this is not a new concept to you. When the speed is changing, you're accelerating. So, instantaneous acceleration in all of this unit, in the whole of this unit, we'll consider acceleration to be constant. It's possible for acceleration to increase, especially in rocket launches and flights, but in this unit, in this course actually, we consider acceleration to be constant. So instantaneous acceleration simply means acceleration at an instant in time. And average acceleration is you get all your accelerations in a journey and average them, that's the average acceleration. So it would be that the total change in speed divided by the time. But again, we're using a constant acceleration in this unit, so don't worry about those two ideas. This little pictorial here is going to help us understand acceleration better. These arrows are representing speeds of cars A, B, C, D, and E. If you look at this car A, the arrows are increasing, right? This arrow is increasing, the arrows are increasing in size. Because the arrows are increasing in size, it shows you that speed is increasing, right? Since speed is increasing, that means that this car is accelerating to the right or accelerating in the positive direction if right is positive. Speeding up, so A is speeding up to the right. And therefore B, if you look at B, the arrows are getting smaller and smaller, so B is slowing down, but moving to the right. If you look at C, the arrows are not changing at all, so C has a constant speed. If you look at D, the arrows are increasing, but in the negative direction. So D is speeding up, but moving to the left. And finally, E, slowing down, and it's moving to the left. So I hope this helps you visualize acceleration. You can be speeding up or slowing down in any direction and still be moving to the left or to the right. Now the trick here is try to visualize this on a position time graph. So this position time graph shows you an object that is, I hope you can see that it's speeding up, right? This object is speeding up because the changes in position, if I try to look at equal intervals of position, I'm trying to get equal intervals, you can see that the change in position gets bigger and bigger for equal intervals of time. If you look at this interval of time, change in position is small. You go to another interval of time, the change in position is getting bigger. And then here, the change in position is even bigger. It's over here where you see that the change in position gets bigger and bigger. So this object is speeding up to the right, right? This one, if we apply the same kind of idea, time, same intervals of time, but I want you to see what's happening to the changes in position for the same intervals of time, right? The changes in position are getting smaller and smaller for the same interval of time, so it is slowing down, but it's moving to the right. And then finally, this one, I hope you can see again that the change in position for the same interval of time, so I have time, change in position is getting bigger, but it's curving downwards. So this object is speeding up, but it's going to the left. Speeding up and going to the left. In your notes, I need you to help me. I need you to draw each of these graphs. So you have that one, you have that one, you have this one, and then you can have that one. You can have, yeah, is that one? Yeah, I need you to draw each of these graphs and describe what they mean in terms of acceleration. If a racehorse is coming out of a gate and accelerates from a velocity of 15 due west in 1.8 seconds, what is its average acceleration? Acceleration is change in velocity divided by time. The final velocity minus initial velocity divided by time. Final velocity is 15 meters per second. It's coming out of the gates, so that means its initial velocity is 0 meters per second, and the time is 1.8. So go ahead and calculate the acceleration. All right, that's it for today.